Good morning, everyone. This is Sachin Fiske from Electrical Engineering Department, SND College of Engineering and Research Center. Today we are discussing about asymptotic approximations. So here some asymptotic approximation of integrals part we are going to start. In the previous lecture we discussed some points related to Bode plot. Let us see. In the first part, we discussed the concept of asymptotic expansion and its importance in application. We focus our attention on special functions defined through integral and consider their approximation by means of asymptotic approximations. So we explain the general idea of theory of asymptotic expansion of integrals and describe the two classical methods, that is Watson lemma and the saddle point method. The modern method, that is distributional method. In the second part, we apply these ideas to approximate or asymptotic sense polynomials of the ASCII tables in terms of simpler polynomials of the ASCII table. Here we consider two different types of asymptotic expansion that have been recently developed. Number one, some parameters of the polynomials is large, or second one is the degree of the polynomial is large. For each situation, we employ a different asymptotic method. In the first case, we use the technique of matching of the generating function at the origin. In the second one, we employ a modified version of the saddle point method together with the theory of two-point Taylor expansion. In the first case, the asymptotic expansion results in a finite sum of polynomials. In the second one, the asymptotic expansion is a convergent infinite series of polynomials. We conclude the paper with the information on other recent development in the research on asymptotic expansion of integrals. So what is basically the introductory part indicates asymptotic analysis is a useful mathematical tool which provides an analytical insight and numerical information about the solution of complicated problems in applied mathematics, engineering, physics, and many other sciences, which require a mathematical framework for describing and modeling scientific problems. So let us consider the asymptotic behavior. This behavior of a function has the input approximation reaches to infinity. Let us take on x-axis the running time for the input, and it is given by capital N, and on y-axis the size of the data we have taken. So the Stirling formula for this factorial is n factorial is approximately equal to n to the power n into e to the power minus root of 2 pi n, and inside the bracket we have to consider it as a 1 plus 1 by 12 n plus 1 upon 288 n square plus so on, that is n tends to infinity. The approximations of the large harmonic number can be considered as 1 plus 1 by 2 plus 1 by 3 plus 1 by n, and its approximation is log of n, so n tends to infinity. The approximation of the solution of a boundary value problem, for example, the solution of this boundary value problem is given in these approximations. So which of these functions is the smallest asymptotically? For finding the asymptotically smallest function, let us consider this h of n and c f of and then g of n and f of n. We can plot this data as per size of the data to the running time of the input size. So these approximate calculations of the electrons that is E response is approximately equals to the 1.60 into 10 to the power minus 19 C. And in general, a practical definition of the asymptotics may be asymptotics, and that is equals to approximation of a complete function of f of n by more simple functions f of z, that is c into f of z, which improving the approximation for large value of a parameter. Let us consider one example, that is log of 1 plus z minus log z into z to the power z into 2 pi z. Means by putting the value of n equals to z here, we have z tends to infinity. So which function is the smallest asymptotic, that is g of n seems to be grow very slowly after a while. Now proving that g of n is equals to 0 into f of n would provide a conclusive answer. So what should be the conclusive answer? A precise definition of this asymptotic and of the simple summation is given in the next section. There are two main areas of investigation in asymptotic. The first one is concerned with the solution of differential equation when f of z is the solution of the second order linear, that is ODE. For example, one solution of the equation z square into omega double derivative plus z into omega double derivative plus z square minus v square into omega is equals to 0 is the Bessel function, that is jv into z, and this asymptotic theory of second order linear, that is ODE, together with the information on initial value, which tells us that the base function, that is jv of z, is approximately equals to 1 upon 2 pi v ev upon 2v whole square, in which tends to infinity. The second area deals with the function f of z or f of n. There are some limits generally we use. So if limit n tends to infinity, g of n upon f of n is a constant value, then we should go for g of n is equals to 0 into f of n, where this constant includes 0 but not includes the infinity value. Secondly, if this limit n tends to infinity, f of n upon g of n is equals to infinity. Let's see here what is given in the first limit. It is g of n upon f of n. At that time, it should not include the infinity. But here, f of n, if we inverse this, f of n upon g of n is equals to infinity, then g of n is equals to 0 into f of n. There should be no limit expansion. If limit n tends to infinity, then f of n upon g of n is constant, then g of n is equals to omega f of n, and again constant is 0 but not infinity. And this is limit n tends to infinity, f of n upon g of n is a 0 is a non-zero constant, then g of n is equals to 0 into f of n. In this definition, both 0 and infinity are excluded. The previous formula relating the limit to big OH, that is Ohm notation, shows once again that big Ohm notation ignores, which ignores constant, then behavior of small value of n. Then how do we see that? Let's see. The asymptotic behavior of the integral for large value agree with one of the j of z as shown above, and of course this integral is nothing but an integral representation of j of z as shown in the previous. Here we present an introductory overview of asymptotic theory of internal integrals and apply this theory to obtain several asymptotic expansion of the polynomial of a ASCII tables. In this, we give a brief introduction to asymptotic and in particular asymptotic theory of integral. Also, an overview of the classical method or integral based on Watson lemma. At present, an asymptotic method to obtain asymptotic expansion and polynomial in ASCII table when one parameter is large. So we derive an asymptotic expansion of some polynomial of ASCII table when a degree is perhaps to be found in the value of the systems. These values of the constant does not matter, but in the previous formula, only the limit at the infinity matters. This means that we can ignore the behavior up to any infinite value if we need to. So the asymptotic theory of the integral, we generally consider one equation, that is n to the power 5 plus 3n to the power 4 plus 2n to the cube plus n square plus n plus 12 upon 5n cube plus n plus 3, which is equals to 0, or what should be the value which we found. We motivate the precision definition of the symbol by means of an example. So f of x is equals to x into integration of 0 to infinity and so on. This integral is not expressible in terms of elementary function and we wish to approximate it for large value of x. So for large value of x and fixed, we should have some limits. That limit should be equals to n square. Let g of n is equals to the above equation. This equation indicates f n to the power 5 plus 3n to the power 4 plus 2n cube plus n square plus n plus 12 upon 5n cube plus n plus 3. Let f of n is equals to n square. So limit n tends to infinity, g of n upon f of n is equals to limit n tends to infinity, whole complete bracket into 1 upon n square. So it is again as same. So on big Ohm transitivity, if g of n is equals to 0 into f of n and f of n is equals to 0 into h of n, then g of n is equals to 0 into h of n. So how can we prove this? It is proved as per this. How can, so using the definition of the code multiplication, generally this g of n is less than c of 0 into f of n for all n greater than or equals to n 0. If f of n is less than c1 into h of n for all n greater than n1. Now we have to set some value, that is c2 is equal to c0 into c1, or value of c0 is equal to c1 upon c1, c2 upon c1. Therefore, n2 is equal to maximum n0 n1. Then g of n is less than c2 into h of n for all n greater or equal to n2. Now there are some substitutions. If limit x tends to infinity, h of x is equals to infinity, then g of x is equals to 0 into f of x, which tends to g into h of x is equals to 0 into f of h of x. Here we use h of x is equals to under root of n. So with that we get log of n is equal to 0 into n, which tends to log of under root of n, which is equals to 0 into under root of n. Some summing factors are given, that is summation are the formula of the sort, that is summation of k to n is equal to 0 into f of k. By computing these values of the summation can be handy when trying to solve recurrence. Oftentimes, this establishing the upper bound is sufficient since we use this old notation. And if we f of k is greater than or equal to 0, then summation of k to n is equals to 0. F of k is less than or equals to summation of k to infinity is equal to 0 f of k. So sometimes summing to infinity gives a more simple formula. Some geometric series are there. A geometric series is a sequence of C of k or C suffix k of a number such that C of k is equal to d into C of k minus 1, where d is constant. So to express C1 in terms of C0, C1 is equal to d into, as d is constant, so d into C0. To express C2 in terms of C0, C2 is equal to d into C1 is equal to d2 into C0. To express Ck in terms of C0, Ck is equal to d to the power k into C0. So to define a geometric series, we just need two parameters, that is d into C0. And by using this, we can easily find out the values of Ck, C1, C2, and so this is supposed to be a review of the material you have seen in math course. Suppose value of x is lies in between 0 to 1, then finite summation can be implemented as summation of k to n equals to 0 into x to the power k, which is equals to 1 minus x to the power n plus 1 upon 1 minus x. So infinite summation can be given as summation of k to the infinity is equals to 0 into x to the power k, and it is equals to 1 upon 1 minus k. Similarly, we can find out summation of k to the power n, k to n, sorry, is equals to 0 into x to the power k is equals to 0 into 1. Now we are moving towards the harmonic series. So h of n is equals to summation of k equals k to n is equal to 1 into 1 upon k. So log of n is less than or equal to h of n is less than or equals to log of n plus 1. The above formula shows that the harmonic series can be easily approximated by the natural logarithm. This expansion is not a convergent and limit n tends to infinity into s into n cube of x does not exist. Then one is tempted to throw the expansion into the garbage and forget about those formal manipulations. Before doing that, let us give Sn of x a chance and the plot of the function s4 of x and f of x together. Surprisingly, even though the series is not convergent, the sum of the first few terms of the series provides a good approximation of f of x for x moderately large, and easy explanation of this phenomenon may be obtained by putting some rigorous in the above formal manipulation. Instead of expanding 1 plus p by x to the power minus 1 as a geometric series with an infinite number of terms, just expand up to the n numbers. Now, to introduce this decomposition of 1 plus p by x inverse into the integral f of x and interchange the summation and integration. That is, s into n of x approximates very well the integral f of x for the large x, although the approximation is not good for arbitrarily large value of n because of limit n tends to infinity n factorial upon x to the power n is equals to infinity. For fixed x, if n factorial upon x to the power n is achieved for psi n plus 1 is equal to log of x. The expansion is divergent, and for given x, the best asymptotic approximations to f of x is obtained by truncating that series in at a term n such that psi into n plus 1 is approximately equals to log of x. It usually happens that this optimal transaction or truncation occurs at smallest term in absolute value of the series. Now, we will give a meaning to the symbol approximate to above discussion. We have function defined in an unbounded set omega of the complex plane. The formal series summation of n tends n to infinity is equal to 0 into phi n z is called as asymptotic expansion of f of z when the value of z tends to infinity in omega. And we can write f of z is equals to f of z tends to infinity in omega. F of z is approximate equals to summation of n is equal to 0 to infinity phi of n into z, where z tends to infinity. Nothing produces the series summation of n equals to 0 to infinity phi of n into z from being divergent. As a matter of the fact, the asymptotic expansion of many special functions are divergent. In the example of the exponential integral studied in this section, this exponent and r of r into n x is given in. This one is just an easy example of which the asymptotic analysis is quite clear. But in practice, to obtain an asymptotic expression from an interesting integral is not always a straightforward task. For this reason, for a long time, several asymptotic methods for integral have been investigated. There is not a general method for this integral and many other methods as we discussed earlier. So we classify them in several categories depending on the asymptotic principle from which they are obtained. Classical method based on Watson, lamina, and summability method, distribution method, Lenin transform technique, integration by part, and so on. So what is classical method for integral based on Watson lemma? Yes, it is impossible to survey here all the method based on Watson lemma. That is Watson lemma, Laplace method, the saddle point method, Perron method, to mention the important one. We just explained in the section of asymptotic ideas connected with this method by means of two well-known examples, the Watson lemma and saddle point method. And intuitive argument tells us what to do to the approximation. This kind of integral for large z as r of z increases the absolute value of the exponential, that is e to the power minus t into r of z concentrates more at t equals to 0. Then for larger value of z, the main contribution to the integral comes from t near 0. Therefore, one hopes that only the value of g of t near t equals to 0 is relevant. Then, once we approximate g of t at t equals to 0, substitute this approximation in the integral and integrate term by obtain. So f of z is equals to summation of n is equals to 0 to n minus 1 a to suffix n into n factorial upon z to the power n plus alpha plus 1 plus rn of z. Therefore, rn of z is equals to integration of 0 to infinity e to the power minus z to into g n of t dt. The integral factor f of x studied in the preceding section is an example of the application of Watson lemma. And for this integral, g of t is equals to 1 plus t inverse gn of t is less than or equal to t to the power n, and Rn of x is less than or equal to n factorial upon x to the power n plus 1. Another way to obtain the asymptotic approximation more prominently than intuitive approximation described above, and it is the just means the change of variable t tends to t of z. The remaining method that we call classical based method on Watson lemma consisting of reducing the integral to another integral to which the Watson lemma may be applied. We show this procedure with the important example on the saddle method. This method, next method is the saddle point method. This method applies to the conduct integral of form where f of z is equal to integration to the base n e to the power z n into omega into d to omega into dw. Z tends to infinity, where L is the path in the complex plane and the function g and h are analyzed whenever it is needed to perform the manipulation described below. The saddle point of the integrand are the point where h of omega vanishes, and this point may give the main contribution to the asymptotic behavior of the function f of z for the large value of z. Other points that may give the significant contribution are the endpoints of the path L, and if these are only finite. In fact, one tries to determine if R of ZH of omega is maximum at one of the saddle points or at the endpoint of L if the saddle point say omega 0 belongs to L gives the main contribution and has is fixed at omega 0. The asymptotic expansion is obtained from the local expansion of h of omega and g of omega at omega 0. This method is also called as Laplace method. If one of the saddle point is not located on L and one has verified that this point will give the main contribution, one tries to deform the path L such that the new path goes through the saddle point, say omega 0. Thank you.